Okay, so I think we can start. So good evening to everyone, and in today's webinar, we are going to talk about um, common errors that people commonly do in STKO and OpenSees, and convergence problems. Now, they are quite large topics, so we are going to focus on not, of course, not on all the possible errors that people may encounter, but only on the main ones, based on what people ask on our forum. So we share my screen. As usual, we are going to record this webinar, and by tomorrow you are going to have all the input files that we're going to use today, the PowerPoint presentation, and the webinar recording on our website. And we are also live streaming on YouTube, on our YouTube channel. Okay, so here we are. Perfect. So let me go on my computer. So here's today's presentation. We're going to focus on common errors and convergence issues in both OpenSees and STKO. Why both of them? Because some errors are strictly related to STKO and to the modeling techniques that you have in STKO. And some of them instead are more finite element based, so they are strictly related to OpenSees. I will try to explain their meaning and most importantly, how to fix them. So these are the contents. First, we are going to talk just a little bit about what are the main source of errors that are due to a wrong modeling on the STKO side. First of all, they mainly depends on a misunderstanding of the geometry module. Here it is called BREP. BREP stands for boundary representation, and I will explain you what is boundary representation, because if you don't understand very well the concept of how STKO treats the geometries, it may lead to many mistakes. Another commonly done error is the wrong property assignment. When you assign properties that are incompatible with the mesh you are using. And this kind of errors can be easily detected by STKO. And so I will show you how this kind of error can be detected and how you can fix them. And of course, there is one common mistake that people do, and there is not so much to say about that, but keep in mind that STKO works on geometry, not on the mesh. So every time you change your geometry, don't forget to remesh your model. Otherwise, you will not be able to generate your TICL files. And then we will spend most of the time of today's webinar about the OpenSees errors, which are instead probably more difficult to understand. Now, of course, there are thousands of errors that can be generated by OpenSees. It will be impossible to cover all of them in just one webinar. So I will focus on what I think, based on what we see on our forum, what I think are the main errors that people can do in OpenSees. And I think that most of them are related to the constraints, because if you do not constrain your model properly, or if you constrain it properly, but you don't know how to handle those constraints in OpenSees, this one will lead to many other errors, non-convergence errors or singularity of the system matrix. And it is not so easy to understand that those errors actually come from a wrong handling of the constraints. And then, of course, there are the convergence errors that everybody challenge every time you do a nonlinear analysis. Okay, so I'm going to start with the errors coming from STKO, and they mainly come from modeling errors. So as I told you, in STKO, well, actually in the finite element world, there are two kinds of user interfaces. One kind of user interfaces, they use the concept of orphan mesh, for example, like SAP or ATABS or MIDAS-GEN, where you basically draw your nodes and your finite elements one by one, and you directly work on them. That is called orphan mesh. Orphan because they do not belong to any parent geometry, because you don't have the concept of geometry. And then there is another class of user interfaces, like STKO or Abacus or COMSOL Multiphysics, where they basically work on geometry, So you draw your CAD geometry, you apply materials, you apply conditions on them, and then at the end of before running your analysis, you measure your geometry, discretize it. The basic concept is that you are not working directly on the mesh, so don't think that you are working on the mesh. You are actually working on a geometry that finally will be converted to a mesh. In STKO, we use the concept called BREP. It's quite popular among the geometric world, the CAD world. BREP stands for boundary representation, and it means that every geometry, every solid geometry or surface geometry, is represented by its boundaries. For example, in this case, I have a solid. A solid is actually a piece of volume that is bounded by a shell. A shell is a collection of faces. So for example, here you can see the a hierarchical representation of this solid here. So solid is bounded by a series of faces, okay? Then every face is a planar element that is bounded instead by linear element. In this case, they are called edges, okay? Some edges, for example, can belong to two different faces. For example, this edge here belongs to this face and this face. And in turn, edges are represented by their boundaries, which are finally the vertices, okay? And then the vertices, they define the spatial dimension. Okay, so now I will show you basically in STKO how you can see this hierarchical representation and how to understand it. And to explain you better how you can, with a geometry that looks the same, actually you can model different things, and or you can make mistakes and you think you're modeling something, but actually you're modeling something else. The one concept that I would like you to keep in mind is that the mesh reflects the geometry. So for example, if you have this joint geometry, the mesh will be this joint, okay? Now I'm going to show you an example where I want to model a beam, actually using surface elements, because it's easier to explain what I want to explain. And I will show you that basically the same CAD model, depending on if you draw them attached or detached, it will be translated into a continuous beam or a completely detached beam or a partially constrained beam, okay? This is very important because I've seen many people that try to model a series of beams, for example, without joining them into a single geometry. And they think they will be attached, but if you have two geometries that are detached, also the mesh will be detached. So many times it will lead to unexpected results or on singular matrices, okay? So let's go back to STKO to show you this first example. So I'm going in the preprocessor here. Okay, that's fine. And let's draw two faces, okay? Let's say I want to model a beam, but I need a cut in the middle because let's say, for example, you want to apply something here, okay? For some reason, you don't want to draw an entire beam. You just want to draw a beam by two pieces, okay? So I can draw a face here. And then the same face, I can actually copy. I can type the copy command and I copy it here. Now, many people coming from a background of softwares like Midas Gen, so all of them based on orphan mesh, they think that when you draw a geometry which is coinciding with another one, for example, here the two edges, they are overlapping, they think that automatically the software will join them. This is actually not true. In STKO, if you have two geometries, they will be detached. I will show you how you can recognize this, for example. But first of all, I want to explain you what I had in this previous slide. So how to understand the BREP hierarchical representation. So as you can see here, you have two faces. If you go on the work tree here, you have the in this node you have the geometry itself, and the image here is showing you that this is actually a face. But as I told you, in a boundary representation, a face is made by the face itself, as you can see this one, and by its boundaries, which are four edges. Okay. Now, if I click on them, you can see all of them one by one. And each edge is bounded by two vertices. Okay. That's why, for example, if you want to draw, let's say, a beam, you don't have to do something like this which is something that you may do, for example, in SAP or in Midas. You first draw the nodes, then you draw the element between them. This is not correct because this beam here, which is this line, it already has two vertices. So these two here are just duplicated vertices. So when you are going to mesh them, these two vertices will be detached from this one, okay? So this is the main concept. So as I told you, in this case, you have two faces and probably you think they're attached. Instead, they are not. For example, if I go under a sub-selection, and let's say I want to select only edges. So I switch off the select entire geometry button and I keep only the select edges. Now, if I click here, there is no problem. There is only one edge because there is one edge that belongs to this face and I can simply select it. But if I try to select this edge here, which apparently looks like just one edge, I click here and actually I can find that there are two edges. The edge number 2 coming from the first geometry and the edge number 4 coming from the second geometry, okay? Which are actually these ones. For example, from the first geometry, the second one is that one. And from the second geometry, it was edge number 4, okay? So they are two physically separated edges, but they're just sharing the same location, but physically they are two different entities, okay? So let's say I keep this geometry like this and I think they are connected. So I go on with my analysis. I create a definition, let's say a ramp time series, not a constant, I want to use a linear. Then I go to physical property. Actually, I don't even need the ramp, I just need a constant because the analysis will be linear. So let me go to time series constant. Then I simply assign two random constitutive models. So I want a ND material, which is linear elastic. Okay, just some random numbers because I'm not interested in that. And I drag and drop it to, let me go back to full selection. I select both geometries and I drag and drop the physical property. Then I go to element property and I want to use a quad element in plane stress and thickness of 1. Select both faces and drag and drop the element property. Okay, now we go to the condition. The first thing that I want to do is to fix the two end edges. So fix, and we go to constraint, single point, fix. We are in 2D, just displacement because we are using a 2D modeling. And I want to fix both X and Y displacement on these two lateral edges. Edge. Okay, so here I have my constraint. Then I want to apply a distributed load on top. So I click on add. This one is going to be load, loads, force, edge force, because it should be a distributed load per unit length. And I'm going to add a load of -10 to this edge and this edge. Okay, so this is fine. Let me just rename some of them. This one is the material. It is not necessary, but it's a good idea to keep your model clean. This one instead is the element. Okay, and this one is the time series. Okay, so fixed load. We don't need any other boundary condition. We just need now to run the analysis. So I first create the recorder. As usual, I go to recorders and PCO recorder and result. I just need to show the displacement now. I don't need any other result. Second step, as usual, is to apply boundary conditions. So I go to model, patterns, add pattern, and I want to add a constraint pattern. We just have single point, just one single point constraint actually. So we go here and we select fix. Okay, so we have the boundary condition. Now we apply the load. So add load, pattern, add pattern, load pattern. This time we select the time series. The edge load is actually a load, so it goes here. and we select load, okay, and okay. And now we're ready to create the analysis object. This is going to be very easy because it is a linear analysis, so static, plain constraint, this is fine, everything. This one is going to be linear. So when you do a linear analysis, you don't have to care about the test command. You need to choose one just because OpenSees needs a test command, but it's not going to be used. So one is equal to the other. Just one-time step because it is linear. We don't need to do incremental analysis, and press OK. Now, as I told you, one of the rules here are don't forget to mesh. Okay. Let's see what happens, for example, if I try to run the analysis without meshing. Let me try to run. Oh, before running the STKO file, actually, I need to save this file. This file here, you will find it under STKO modeling errors, brep joint. Then I will show you other two examples. Okay, so these three here are already made. I'm going to create another folder just for this sample file. Sample model. So this one, I'm going to call it this joint. This joint. In this example, I want to show you what is the error when people think that two geometries are attached, but actually they are not. Okay. So let's say someone expects a continuous deformation on this beam, while you're not going to have that. Okay. So first of all, I want to show you the error about the meshing because it is not pretty clear. But if you forgot to mesh it and you try to write a STKO file, you will find an error like this. First of all, I want to show you how the error window works. So first of all, you have the error here in red, which sometimes it is clear, sometimes it is not, because actually this error comes from Python. So unless you're a Python user, you don't understand it. So here it is, you can see key not in C++ map. But if you don't understand this error, you can actually look here at the traceback. The traceback is actually a list of places in which this error has been generated. And here it's quite easy to understand that it depends on the mesh. If you can see here, I'm trying to get a mesh, but the mesh is not there. Okay, the key for that mesh is not in the map. This actually happens when you forget to mesh. Actually, it's very easy because if you go on the mesh tab and you don't see any mesh, you see just transparent geometries, it means that you don't have a mesh. Now, keep in mind that just before running an analysis, you have to build your mesh. And every time you change your geometry, the mesh will be deleted, so you need to remesh it, okay? So now in this case, the mesh will be very easy. I'm going to create a uniform by size of dimension, let's say 5. Done. And then I want to use quadrilateral elements. Okay, so structure quad in both faces, assign, done. And then I can mesh it. Perfect. Now I can save the file. And I can run the analysis. Okay, now the analysis is fine, successful, but it will give me the results that I was not expecting, because if I go on the post processor, I thought that beam was continuous, but it is not. Sample model result. As you can see here, the two beams are actually detached. Why? Because in STKO there are two detached geometries. Okay, so the mesh will be detached, and in the results you will see the bending of actually two separated cantilever beams. Okay, so how do you solve this one? The first option is to go in geometry, and let's say, okay, I want them to be continuous. I just need to select both of them and do a Boolean operation. Okay, so here what I have to see is just one geometry if I want it to be continuous. Now there are two ways for doing this. The first one is the most generic one, is the merge command under Boolean operation here. Merge is the most general operation for merging different geometries, but it works for every kind of geometry. It works for vertices, for edges, for faces, and for solids. And of course, it is more expensive. If you're trying to join only faces, you can use the SUFaces command. Or if you want to merge only frame elements, you can use the make wire. If instead it is a mix of many kinds, many different types of elements, for example, you want to merge a face with a line, then you go with the merge command. Now in this case, there are two faces, so I can use this SUFaces command. I press OK. Now, as you can see, I have just one geometry here, which is this one, okay? And differently from before, if I go and see at the edges, now I don't have 8 edges, because before I had 4 edges for every face. Now I have a total of 7 edges, because the 2 edges that were here, they were overlapping, and due to the Boolean operation, now they are collapsed into a single edge. In fact, if I go here and I try to select the edge, STKO doesn't ask me what edge do you want, because there is just one edge, okay? So this one is one opportunity. As I told you, I changed the geometry so the mesh disappeared. I just need to rebuild the mesh. And if I run the command, if I run the analysis now, I just go back to my results, I reload it, okay? And now the results is as you expect, okay? Because now the 2 geometries are actually being converted into just one geometry, and so the mesh is continuous, okay? So you may ask, why don't you do that automatically? For example, when 2 geometries are overlapping, are coinciding, why don't you automatically join them? Well, because there are cases in which you actually want 2 overlapping geometries to be separated. For example, because you want to create partial connections. And just to give you an example, if I want to come back to my 2 separated geometries, I can use the explode command. Okay, now they are back to 2 separated geometries. And so one reason for which you may need to keep these 2 geometries separated is because, for example, you want to create an interaction between them. Now, let's say, for example, you want to only the top node should be continuous, while the entire edge should be discontinuous. So how do you do that? You cannot use a Boolean operation, otherwise everything will be attached. You cannot leave it as it is, otherwise everything will be detached. So you need an interaction, okay? So in this case, we are going to create an interaction, and we can call it link. It is a node-to-node interaction. And I want to select only vertices, because I want to attach this vertex to the other. Okay, so I go here, I click. Now in this case, I have 2 vertices, as I told you before, one coming from the first geometry and one from the other. So I pick one of them as the master, then right-click, and I click on the other for the slave, right-click. And here I have my interaction, okay? Now, for example, if I try to move this geometry away, you can see that the interaction is actually here, okay? Okay, so here you see it as a point just because there is no gap between them. Okay, now I have the interaction, but it is not enough, because if I want to use this interaction to attach these 2 geometries in this point, I need to create an equal dot constraint. So I go under condition, and I create an equal dot constraint. So I go under constraints, multi-point, equal dot, and I want to attach both degrees of freedom. So I select this interaction and press OK. Now the equal dot has been created, but as you can see, it is black. It means it has been assigned, but it is not blue like the other ones, because it has not been added to the constraint pattern. So I go here, and as you know, if you don't add it to the constraint pattern, it will not be in the analysis, okay? So I go here, I make room for 1, and I select equal dot. Okay, now I save it. I run the analysis. I need to remesh it, as I told you before. Forget to mesh, you just rebuild your mesh. And run the analysis. Okay, now I go back to the post-processor, I reload it. And what I obtain now is a mesh that is actually connected in this point and disconnected along the entire edge, okay? So basically, this one is the reason why you should take care about how you model, because apparently it looks like the same, but depending on the Boolean operation that you have done, you can model different things. So this one is one of the main errors that I see from people. Sometimes I see something like this, as I showed you before, for frame elements. They first draw points, okay? Then they draw lines to connect them, and this is wrong, okay? If you need, for example, 2 lines connected together, you just do a wireframe like this, okay? As you can see, this one is a single geometry, so the node in the middle will be attached. Okay, so basically this is the concept related to the STKO modeling about the misunderstanding of the boundary representation. And of course, I already talked about the fact that you don't have to forget the mesh. Now there is another commonly done error, which is the wrong property assignment. that is somehow related to the boundary representation, okay? Now, as you have seen before, so I go back to the property visualization here. Now, this model was very simple, and so I could simply, when I was here with full selection, I could select the entire face and drag and drop the element material, and it was fine. Why? Because when I select the entire geometry, STKO understands that I want to assign this property onto the highest entity in the boundary representation. Now, since this is a face, the higher entity is just this face here, okay? But if for some reason I'm not in the full selection geometry, but I'm in the sub-selection, and I select this face, and also for mistake, I select this edge here. Now, as you can see, I also have the edge selected, and I drag and drop the element material, the element property, sorry. And if I try to select them, I do select, and you can see that I have selected one face, two face, and the third edge here. This one will give me an error. Why? Because basically now assigning an element property to the edge of this face explicitly, I'm telling STKO that here I want to use this edge, not because it is a boundary of the face element, but because it needs to be another element. So I'm explicitly telling STKO to generate an OpenSees element from that. And this element should be an SSP quad. Now, of course, this is a mistake because in STKO, this one is a line element. So I cannot assign an SPP quad to a line element. Now, if I try to create the input file, I will have an error like, oh, I need to remesh first. And then I run the analysis, and I have this error here. And I think I have it here, this one, okay, which is the second step. As I told you before, the first thing that you have to do is to read the error in red, okay? In this case, the error is quite clear, so you don't need to go down here. The errors say, okay, the spatial dimension obtained from the element module, and the element module is this file here, this the element property, basically, should have the same size as the number of nodes in the mesh element. And here there is a detailed explanation. The element module expects 4 nodes because it is a quadrilateral element, so it needs 4 nodes. But the mesh element has 2 nodes. So here you can easily understand from this sentence that for some reason you have assigned a quadrilateral finite element formulation to a 2-node line element, okay? So this kind of error is quite clear. So you just need to understand, to read the error, understand what is the element property that has been assigned to the wrong geometry. And you can easily find it by just clicking on the element property, click on select, and you can understand, you can visually see what is the selection here. And here you can see that I have selected an edge. So you can easily spot this error. Let's say this one is one of the most commonly done errors in STKO. So now we are done with STKO because I want to leave the last 30 minutes to OpenSees because probably it's more interesting for you. Now, there are many errors that can be done in OpenSees, as I told you. So here I decided to select what I think are the most commonly done and the least understood by the users. And I think, in my opinion, that the constraints are the main source of errors because, first of all, OpenSees gives you the opportunity to use the so-called constraint handler. So in OpenSees, how the constraint works. You first need to create the constraint, okay? So for example, in STKO, when you create the constraint here, or in the TCL file when you write it manually. And then there is a second stage that actually is done inside OpenSees, which is, of course, the boundary condition should be applied to the system matrix. Now, of course, you as a user, you cannot, I mean, it's not you that you have to apply the boundary condition to the system matrix. But the way the boundary condition, the constraint, is applied to the system matrix depends on the constraint handler. And this is your choice, because every time you go in the analysis here, you have the so-called constraint handler, and you have to choose one of them. There are 4 of them in total. And each one of them has advantages, disadvantages, or some limitations, okay? Now, there is a documentation on OpenSees about this one, but I've never seen a course on how to understand the constraints, because you need to have a finite element background to understand how they work, okay? So I will try to spend most of the time now on the constraints, because based on what constraint you choose, even if you create and assign the constraint properly, if you choose the wrong handler, it can lead to non-convergence or actually singularities, okay? Or even if the model converges, it will give you a result that you are not expecting, okay? So first of all, let me go to the next slide, which is a summary of all the constraints that you have. Now, first I will give you this summary, and then I will explain all these problems one by one using examples. Now you have 4 types of constraint handlers. The first one is the plane, then you have the transformation, then you have the method of the Lagrange multipliers, and then you have the penalty method. Now, by default, STKO chooses the plane because actually there is not a unique choice here, because each one of them has advantages or disadvantages. So you need to understand it very well. There is not just one constraint handler that works in every case or without paying attention. So the first thing that I want to say is about plane and transformation. Plane and transformation, they have some common rules, some common features. Both of them, they do a matrix condensation. It means that some of the degrees of freedom are eliminated from the global stiffness matrix. So the main advantage is that they reduce the size of the stiffness matrix. How does it work? For example, if you have a single point constraint, for example, if you are fixing the displacement of a node, that row in the system matrix will be eliminated. Or if you have multi-point constraints, the slave equation will be eliminated in favor of the master equation. Okay, so both of them has this concept of condensation of the slave doves. But since you have you need to remove some of the rows, you need to pay attention in the multi-point constraints to the master-slave pairs, okay? And I will show you with a practical example what it means. For example, if you choose a wrong master-slave pair, it will lead to different results or actually singularities. It is pretty clear because if you think that they have to remove an equation, and for some reason a certain equation is laid of 2 different masters, you understand very well that in the first case it will be eliminated, but when the second constraint has to be applied, there is no row to condensate because it has already been condensed, okay? Then these 2 points are in common between them. Then the transformation is pretty general. So except from the fact that you have to pay attention to the master-slave pairs, there is no other limitation. While the plane constraint handler has two limitations. It can be used only for homogeneous single point constraints. What does it mean? An homogeneous constraint is is a constraint that imposes a solution equal to 0. For example, a fixity. Okay, when you say displacement of node 1 is equal to 0, that is an homogeneous constraint. But when you use, for example, an imposed displacement, for example, you say that the x displacement of node 1 should be equal to a finite number, not 0. For example, it should be equal to 1. That is a non-homogeneous constraint, and it cannot be handled by the plane handler. This is quite easy to understand because the plane handler gives you a warning, okay? But it doesn't stop. It stops the analysis. So it just writes a warning, and if you don't pay attention to that, you keep on running the analysis and you don't see that error, okay? So always have a look at the entire output from OpenSees. Then there is another problem about the plane. It can be used only for constraints that have an identity matrix. I will show you how it works, but basically every single point constraint is fixing an element on the diagonal. So it is just a scalar, so it is also an identity matrix. But the only multi-point constraints that generates an identity matrix is the equal dov, okay? Because you say displacement of node A is equal to displacement of node B. So the constraint matrix, if you look at the matrix formulation, is equal to an identity matrix. For example, the plane cannot be used with the rigid diaphragm, because the rigid diaphragm says that the displacement of a slave node is equal to the same displacement of the master node plus the distance times the rotation of the master. And this distance times the rotation actually is an element that goes out of the diagonal of the constraint matrix. So the constraint matrix is not identity and it is not diagonal. So it cannot be handled by the plane constraint. Okay. So these two here are the two limitations of the plane with respect to the transformation. Of course, the plane is much faster, while transformation takes a little bit more time. So let's say this one is the most general one, but there is a problem. When your model gets complex, you have to pay attention to the master-slave pairs. So the first thing that I want to show you is this one. Okay. With the plane, you have to take care about these two extra limitations. Then we move to other two kinds of constraint handlers. They probably are a little bit more complicated to understand, but I will show you with some examples how they transform the matrix. So none of them do matrix condensation. So the first drawback is that you do not reduce the size of your matrix. Actually, the Lagrange multipliers does the opposite. It adds one equation for each constraint equation. So instead of eliminating the equation, it actually adds an extra equation. I will show you how these extra equations are added, but in the way they are added, they transform the matrix in a way that if the matrix was positive definite means that they have all strictly positive eigenvalues, the final matrix will not be positive definite anymore. It will be symmetric if the original matrix was symmetric, but not positive definite. And this one can give you a problem if you choose, for example, a solver that is SPD. SPD in OpenSees stands for symmetric positive definite. Okay, so you have to pay attention to the to the solver that you use. Then, of course, also here you have to pay attention to the master-slave pairs, not because there is the condensation, but because if you apply, let's say, a node is slave of two different masters, you are creating two constraint equations that are somehow linear dependent, okay? So the system is said to be over-constrained. And then you have an extra problem here, which is common to the penalty one. That's why it is in orange. With the Lagrange multiplier method, if you know how the Lagrange multiplier works, you cannot use a convergent test on the displacement. Why? Well, you need to have a little bit of background on constraining equations with Lagrange multipliers. But basically, with the Lagrange multiplier, in these extra rows that he's going to add, the solution vector, which is actually the displacement and rotation vector, it has in those rows the constraint forces, okay? So the problem is that if you try to test on the convergence from displacement, you have to understand that in that vector, you also have forces, okay? So it will be very difficult to reach convergence in that point. And then you have the penalty. Penalty is the one that I prefer because probably there is only one key point where you have to pay attention. It doesn't change the system size in the sense that it does not do any condensation, but it doesn't add any extra equations. So the size of the system matrix is the same size of the matrix without any constraint, okay? And that is fine. Similar to the Lagrange multiplier, you cannot use all the convergence tests, but it's the opposite of the Lagrange multiplier. In this case, you cannot use the test on the unbalance. You have to use the test on displacements because the penalty is actually like adding very stiff springs. So if you check the unbalance, it will have the constraint forces that will never go to zero, okay? So if you try to check for convergence on the norm of the unbalance, you will never reach convergence. So the only drawback of the penalty is that you have to pay attention on how you choose the penalty parameters. I already talked about this in previous webinars, but the fact that I like it is just because it is a simple rule. There is a simple rule to understand how to choose the penalty parameters, and I will explain it to you later on. Okay. So first of all, now I'm going to show you an example, a practical example of a column with lamp plasticity, okay? And I will show you that how important is to use the master, to pay attention to the layout of the master slave pairs for plane and transformation, okay? Okay, so let me create a new file. Actually, I don't want to create it from zero, otherwise I spend too much time. I will start with this one, constraint errors, wrong master slave pair. I already have it here. So this one is very simple. In the geometry here, what I have just one beam here and 2 points. Why in this case I draw two separated points? Yes, because I want to create an hinged beam, a plastic hinge there, okay? So if I move this one just for the sake of simplicity so that I can visualize the connection between them, if I move it on one unit here, you can see that actually this beam is detached from these two nodes, and the top nodes here, the top node here is connected to the top node of the beam with an interaction, and same thing for the bottom nodes. Okay, I do this because here and here I want to apply some plastic hinges. Okay. Now, you know, if you have seen previous webinar about STKO, you know that we use the hinged beam for that. So you don't need to create the extra node separately. But in this example, I want to show you the manual way to create a lamp plasticity column, because this example is very convenient to understand the error about the wrong master-slave pair. Why? Because in the hinged beam, we already take care of choosing the right master and slave pairs, okay? Okay, so first of all, let me just remove this one. Okay, so let's say you are modeling a beam. So you do your beam here, you assign the property, you do everything you need, you create a spring for the nonlinear plastic hinge. In this case, they are simple modified Ibarra, okay? Then you create the zero length element property with only a degree of freedom activated, which is the rotation about the global y, the global y direction, because I'm going to push the column in the x direction. And then I have an elastic beam column to be assigned to the internal column and a zero length element for these two interaction that I'm going to create, okay? Then I have some fixities and I will explain you one by one. So first of all, let me create an interaction. So now let's say that, let me call it hinges. Okay, now the interaction, I need to select master nodes and slave nodes. Now, what do I choose as master and slaves? If you don't know the background about matrix condensation, for you it's the same, because you may say, okay, but saying that displacement of this node is equal to the displacement of this is the same as saying the displacement of this one is equal to the other. So you may think that choosing what is the master and what is the slave doesn't make any difference. Instead, it is not like that, because from a computational point of view, there is a difference, okay? So let's say that I choose this one as the master. So the node of the beams are the masters, okay, so right click, and the other nodes are the slaves, okay? So from a theoretical point of view, it is perfect, that's fine. There is nothing wrong about that. But from an implementation point of view, so based on how OpenSees has been implemented, this is wrong, okay? So you should choose this one as the master. Now let me choose this one as the master, so I will show you what is the problem. So here I select them and I drag and drop the zero length material, and once again I select them and I drag and drop the zero length finite element. And then, of course, as I told you before, the zero length has a spring only in the rotation about the y-axis. Everything else is free. So we need to use an equal dot for that, okay? The equal dot will fix all the other degrees of freedom, but not the rotation about y, because here we have an hinge. So I select the other two, this one, and I drag and drop the equal dot. Sorry, I don't have to drag and drop because this one is a condition, so I simply edit it. And before pressing OK, I click these ones. Okay, so now I have also the condition here. Now all the other boundary conditions, just to explain it to you, I have a fixity in the bottom. Everything is fixed on this node. Then I have a fixity on the top where everything is fixed but the x-axis. So actually this one is moved in shear without allowing the two ends to rotate or to elongate, okay? So it can only move in shear here. Then I have an horizontal load at the top, okay? So here I'm just going to do a pushover analysis on this node here. So these are all the boundary conditions, and of course the equal of to impose the continuity in all the degrees of freedom that are not the plastic hinge that I want, okay? So everything else is pretty clear. So I have the recorder, I have my constraints, and as I told you, I have two single points constraint, the fixity at the two bottom and top, and here I have the equal of for the plastic hinges. Then I added the horizontal load with the linear time series here, which is a ramp. And then I have my analysis here. So let's say I start with a plane constraint because I say, okay, I don't have any particular multi-point constraint. I don't have homogeneous, non-homogeneous constraint, so I can use the plane constraint, okay? So I only have equal dofs, so this is fine. I don't have non-homogeneous constraints, so this is fine. I only have to take care about the master-slave pairs, okay? So the plane is fine. I just use any kind of number. In this case, I want to use a displacement increment test, but I could use also the others. And then I do a load control, okay? Now, before running the analysis, I want to move the beam back in place, because as I told you, I moved it here just to visualize the interaction. Now, before running the analysis, I need to move them back in their place. Perfect. Then I need to mesh and to run the analysis. Now, at a certain point, this one will not convert just because, okay, this is fine, but oh, actually here it cannot converge because as I told you, I'm using the constraint. So here, this one is exactly the error that I want to show you. It is saying, let me go to the very beginning. First of all, the error is saying that the solver that I choose, it cannot solve the matrix, it cannot factorize the matrix because it is singular. It is saying, for example, the diagonal element at 0, actually at row 7, is equal to 0, okay? And then in many other rows, they can be like that. But basically, it is saying, I cannot solve your problem because the matrix is singular. But why? Actually, here you have a warning that can tell you the reason for this. It is saying that this warning comes from the plane handler, so you already understand there is a problem related to constraints. And it's a constraint at degree of freedom 0, so displacement x. It is already specified for constraint node in multi-point constraint at node 1. So basically it is saying that the x displacement of node 1, you are trying to fix that degree of freedom for both a single point constraint and a multi-point constraint. And this is actually the case here because the bottom node of the beam, so if I go back, if I move it back, it is referring to x displacement of the first node, which is this one at the bottom. Since this one is the slave, because if you remember, when I created the interaction, I said that this one was the master and this one was the slave. So what I'm saying is that the displacement of this node should be equal to the displacement of this one. So this one is a slave. And as I told you, the plane constraint angler will try to eliminate the degree of freedom of this node in favor of this one. But then I also saying that I want to fix this degree of freedom. The problem is that OpenSees cannot do that because it can only apply one of the two constraints, okay? So that is the reason for this warning. Now, fortunately, if you use the panel, the plane constraint, it gives you this warning. So if you already understand how OpenSees works, you can easily realize that the error is due to the constraint handler. But actually, I want to show you that this is not a rule because if you choose the transformation, and I can make sure that the problem is the same, but if you choose transformation, it will give you exactly the same error. Let me move it back to its position, and I remesh it. But if I use transformation, I don't have any warning, I don't have any warning, so I don't understand that the problem is coming from the constraint, but actually the problem is the same. It is saying that the factorization failed because my matrix is singular, okay? So exactly the same problem, because as I told you, they work in the same way. Both of them try to condensate the slave, the slave node DOFs in favor of the master DOFs. With the problem that the transformation doesn't give you any warning. So you do not, if you are not familiar with OpenSees, you do not understand that this singularity is coming from a constraint. And I've seen people that think that this singularity comes from the nonlinear material that they have or many other things, but actually they just come from a wrong constraint handler. Just to show you that, I simply, let me go back, let me move it back. Now I remove this interaction, and I do the opposite. I do the same interaction, but now I want to select the exterior nodes as the master and the interior node as the slaves. Why? So why I have to make this decision? Because the exterior nodes is the one that is involved in two different constraints. So this node should be fixed on one side and should be attached to the other node on the other side. So since this one belongs to two different constraints, this one should be the master, okay? I cannot choose the other one. If I do this, so I first select this one as the master and then the other as the slaves, you will see that the analysis will go properly. So I drag and drop the material model, I drag and drop the element model, and the constraint, the equal dot constraint, add it. Of course, I have to do it again because I simply deleted the previous one and I created the new one. Okay, so now I also have my condition. I move this back to its original position. Okay, then I mesh it and I run the analysis. Okay, now the analysis is going. At a certain point, 90%, it doesn't converge, but just because I'm using a load control, okay? So this is fine, and the same thing happens if I use the plane constraint. Transformation, I go back to plane, because for this particular example, they work the same, okay? I reach 89% and then it stops. So basically, as you can see here, just changing what is the master and what is the slave can make the matrix singular. So this one probably is one of the most commonly done errors. That's why I prefer to use the penalty, because for the penalty, there is no difference. What is the master and what is the slave? Now, in this example, I've used the plane and the transformation just to explain you this error here, okay? So you have to pay attention to this one. Now I'm going to talk about, very briefly, because I want to talk also about the convergence issue, about the other features of the other constraints. And I will spend just 5 minutes for this, but I will show you that I will give you a file that will print the entire system matrix on a very small model, of course, so you can understand how they work, okay? So just let me give you a brief summary. And the file that I'm going to open is actually, if you go here in OpenSees Constraint Anglers, you have print matrix. This one is a very simple file with a script that allows you to write to the terminal in a pretty formatted way the entire stiffness matrix, so you understand how the different constraints, how they transform the final matrix, okay? So let me open the print matrix file. This file is very simple. You have just one truss in the middle, which is this one. Okay, one line, one truss. Then you have a ramp here. Then to make it very easy to understand, I created a uniaxial material with a unit Young modulus and a truss section with a unit area, okay? In the way that the EA, so the actual stiffness of this one, and the length, of course, is 1 of this one. So EA over L is equal to 1. So it's very easy to visualize the stiffness matrix. Then I choose a truss element. This problem is in 2D. So I apply the pin here, fixing both degrees of freedom, and a roller on the other side, fixing only the Y degree of freedom. And then I have a force in the X degree of freedom of the free node. So as you know here, basically this one is a single truss in 2D, so it has 2 degrees of freedom per node. So the system matrix without any constraints should be a 4 by 4. Okay, now just to show you how it works, here in the analysis, I've set up the analysis in a way. Let me start from the plane constraint. I set up the analysis with the full general solver because this one is the only one that allows you to print the matrix. Okay, the analysis is very simple because it is linear. Just I put here 0 times steps because I wanted to do something. Since some combination of some constraint handler will not allow you to run the analysis, I decided to not to do any analysis here. So just set up the analysis and then create a simple script that before running the analysis prints everything. Okay, and then it does just one step of the analysis. Okay, and the analysis will be printed to the file. If it can't, because you are forced to change the solver, it will say, okay, I cannot print the system matrix. Okay, now I will show you how to utilize it. Let's say, for example, that you don't want to use any boundary constraint. For not using it, for example, I can move it to the end in such a way that here my matrix will be singular, of course, because there will be no constraint. But at the point that I print it, you will see how the entire stiffness matrix looks like. So the original unconstrained matrix. Of course, the analysis here will be singular, and this one is the 4 by 4 matrix that we expect. Of course, this is a truss. It has only axial stiffness, so only the first degrees of freedom has k, k, minus k, minus k, okay? And all the other rows are 0, as expected. Okay, now I want to apply boundary conditions. Only this one, actually, this one is not needed. In this boundary condition, I apply both the fixity on one side and the roller on the other side. Now, the fixity will remove both degree of freedom on the first node. The roller here will remove the y degree of freedom on the second node. So what you obtain actually is just one scalar, okay? Because I'm removing 3 degrees of freedom out of 4. So if I use in the analysis the plane, you will see exactly that. My matrix will be just one scalar. And you have it here, okay? Just the one belonging to the stiffness of this point. If I use the transformation, I obtain exactly the same thing. So I go back to analysis. And I run the analysis, and you will obtain exactly the same thing, okay? Just one. So as I told you, this one confirms the point that I put here. Both of them, they do static condensation, okay? Now let's go to the penalty and Lagrange multiplier. So the penalty, here I told you that it doesn't change the system size, okay? But you have to pay attention to the penalty parameters. Okay, let's go back here. And I go to analysis and I choose penalty. The penalty parameters that you have to choose are here. Now in this example, I can choose any number because they are on the diagonal. And when they are on the diagonal, there is no problem. But when you have rigid links or rigid diaphragms where you have out of diagonal elements, the size of this number, it plays a role. Now there is a simple rule to follow. You need to understand what is the highest stiffness component in your matrix. Now in my case, it will be 1. And this value here should be the order of magnitude of that, which is 1, plus 8. So in this case, I should have chosen 1 to the power of 9, okay? But in this case, it is not important. I just want to use this high number so that you can see it in the printed matrix. Okay, now just to show you how it works, I run the analysis. You will see that I still have a 4 by 4 matrix, okay? But I have all these numbers, 1 to the power of 18, on the diagonals, and on the degree of freedom that I decided to fix. I fixed the x of the first node, the y of the second node, and the y of the third node, while the x here is free to move, okay? So this one is what the penalty does, okay? So it doesn't change the stiffness matrix, and it is fine, but it also doesn't increase the size of the matrix. The only thing that you have to take care of is the number here, okay, because it can give you problems. And the other point is that you cannot use a convergence on the unbalance. Now in this example, it is linear, so I cannot show it to you, but these high numbers will also be on the residual vector when you do a nonlinear analysis. And in that case, the residual vector will never go to 0 exactly. So you need to check the displacement vector instead. Now let's try to move from penalty to Lagrange multipliers. So instead of penalty, I choose Lagrange. Now in Lagrange multiplier, you have, by default, it uses a constraint matrix made of ones, okay, by a series of 1 here and there. Then I will explain you how it works. But here I want to choose a different number, let's say 2, just to show you where it places those numbers, okay? So there is no need in real life to choose 2 here. I just do it to show you where those numbers will be placed. Okay, so now as you can see, my matrix is much larger. It's not a 4 by 4, but it's a 7 by 7. Why? Because it is adding exactly 1 row for each constraint equation, okay? And another thing that I want to show you is that, for example, here I have my original matrix. So 1, 1, minus 1, minus 1. Then I have this row and this row, and this column here equal to 0, related to the y degree of freedom of my model. And then for each constraint, I have bound matrix. For example, here I'm saying that the x displacement of node 1 should be equal to 0. The y displacement of node 1 equal to 0. Then I don't have a third column with a number here because the y of the second node, the x of the second node is free, while the y displacement of the second node is fixed. So once again, I have a constraint handler here, okay? So this one is fixing what? The y displacement, and you see it from the column of the second node. Now, as you can see here, you see those two, just because I've chosen 2 on my user interface there. But the thing that you have to take care of is that here you have all zeros on the diagonal. So for every equation, you just fill this side of the matrix, okay? And here you have a quad equal to the number of constraint times the number of constraint equal to 0. The fact that you have these numbers here will place some 0 eigenvalues on the stiffness matrix. So the huge problem here is that you cannot use an SPD solver. And I see many people using SPD solvers in simple examples in OpenSees because they know that their matrix is symmetric, so they want to they don't want to waste time, and they try to use a fast solver, which is an SPD. But the problem is that now, so I want to show you this point here. The system matrix is not positive definite anymore. If I'm using the Lagrange multiplier here, and I choose, instead of a full general, I choose one of the SPD, for example, the band SPD or the profile SPD. A lot of people, I've seen a lot of examples in OpenSees where they use the profile SPD. SPD stands for symmetrics, and is okay, and positive definite. This is fine, but a model is not always positive definite. It is positive definite when it is elastic or when it has strain hardening. When it has softening, it is not positive definite anymore because it has negative eigenvalues. When it has plasticity with non-associated plasticity, for example, for those of you who are in the geotechnical field, it is not symmetric anymore. So you cannot make sure that a model is always symmetric and positive definite, okay? But in this case, let's say I want to use this one. I try to run the analysis, and it says that there is a problem. It says that my matrix is singular, but actually it's not singular. It's not suitable for that solver, because for that solver, a non-positive definite matrix is like a singular matrix, okay? So this one is one of the other problems of the Lagrange multipliers. Then what else? I think I explained almost everything. This one is pretty difficult to explain now because I need a very complex model. So this kind of point here cannot really happen in OpenSees because if you are applying 2 equal constraints to the same node, with the Lagrange multiplier, you will have 2 linear dependent equations, and so your matrix will be singular. But fortunately, in OpenSees, they detect this error before you do it. For example, if I duplicate this one and I place it here, I imagine that I have an extra 3 rows because I'm applying the constraint there twice. So the first 3 constraints and then apply other 3 constraints at the same place. But fortunately, OpenSees doesn't allow me to do that. As you can see here, it says I cannot add a constraint which is already fixed. So this is fine. Okay. And the problem about not using the convergence of the unbalance on the penalty method, I've explained it in almost all our webinars. Okay, in fact, I always use the test on the displacement increment. So let's say that this one covers almost everything you should know about constraints, which for me is the main source of errors in the analysis settings. Then the next step, the last step, and I think in 10 minutes we can finish this one, is about convergence issues. Okay. Now, there are many sources for convergence issues. Once again, I will not be able to explain everything. What I want to explain here is actually not when you have convergence problem in the sense that your model does not converge, because that is almost fine. You know that your model is not converging. You try to change the settings. For me, the most subtle problem is when you have convergence issue in the sense that your model converges even if it is not in equilibrium. Because if you're not sufficiently expert in OpenSees, you will say, okay, my model converges, so the solution is fine, but actually it converges to a non-equilibrated solution. It can happen sometimes. And I have an example here, which is taken from our forum. There was our user that was found this kind of problem, and we decided to show it here. So let me open that file. Oh, and you will find the file always in here in the OpenSees convergence errors. Okay, you will find an elastic model and a plastic model. Okay, the two of them are the same. I want to show. Actually, this guy was doing a comparison between OpenSees and ADAPS, and he found that his model was converging to a wrong solution. Okay, and I will show you how you can fix this kind of problem. So starting from the elastic model, I go to convergence errors. You can start from the elastic one, so you can understand what we want to model here. It is a simple column, the same one that I was using before, but without any plastic hinges. Okay, so in this case, it is a simple elastic column, so just one line and 2 nodes. And here you have sign acceleration. Here we're going to put this one as an acceleration at the base. Then we have an elastic section, elastic beam column, some mass in the x or y direction of the top node. Then we have the 2 fixities that I've shown before. So bottom node is completely fixed. The top node is free only in x direction. Then we have a recorder. We have the constraint. We have a first analysis. Actually, here it is not necessary because we don't have any vertical load, and we don't need any wipe here. Actually, I will make it simpler. Then I apply a uniform excitation at the bottom and a time history analysis here. This one is a transient analysis, plane constraint, because in this case it is fine to use the plane constraint. Band general solver, and I try to start with the Newton and the displacement increment test. Now in this case it is not a problem because my model is linear, so I know it will give me an exact solution. So I press OK, just run the analysis. Okay, now the analysis is done, and I'm going to the post-processor to extract some data that we are going to use for comparing the elastic response with the plastic one. Okay, so I go back in convergence errors. I start with the elastic one. Of course, the elastic doesn't have any convergence issue, but I just needed to extract some reference data. So first of all, I want to extract the displacement at the top node. So I go to chart data on nodes, stage 1, which is the only one that I have. Displacement along the x direction versus the time step. Next, next, and I call it UX elastic. And I want to create a chart here. So this one is the elastic displacement versus time. Perfect. Now I do the same, but for the base shear. So here I go to reaction force along the x direction, next, and this one is fx elastic, okay? And then I do the same at the base for the bending moment. So next, reaction moment, this time is reaction about the y-axis, okay? Because I'm pushing along the x, so I want to see the moment about the y-axis. Next, and I call this one my elastic. That's perfect. Okay, now just a simple check. In this case, for the boundary conditions that I have here, I have to make sure that the base moment is actually equal to the shear force times half of the height of the column. In this case, the column is 2.6 meters, so 1.3. If I look at the, well, first of all, I can superimpose the moment here. So you can see that actually they are the same, just scaled, okay? And it makes sense. I remove it. I just want to check the numbers. So for example, if I do, let me open a calculator. So if I take the first one, which is 0.4484 divided by the value that I have in the reaction forces, 0.3449, I have 1.3 with some round of error, but it is fine. And this is true for every component here, okay? So you always have to make sure, even if it is obvious, you always make sure about the correctness of your results, because sometimes if you accept, well, in this case it is linear and it is fine, but if you are doing a nonlinear analysis, it may happen that you accept a convergence with an error which is not exactly zero, and you may obtain solutions that are not equilibrated, which is what it is going to happen now. Okay, so now I unlink all these charts from the database and I remove this database, okay? Because now what I want to do actually is to run the plastic model and show you what happened to this user. He was not obtaining an equilibrated result. So I save this one and I open the plastic. Now, as I will give you the plastic will be the settings that do not work, okay? So you can follow this webinar to understand how to fix it, okay? So the model is exactly the same. You have the same sinus acceleration, same elastic section for the beam. Now the beam is still a beam with two nodes here, but we are using the injet beam. So it will generate automatically the plastic hinges at the top and the bottom, okay? So I have an elastic section here. I have a stiff material here. The stiff material is chosen in such a way that it is a couple of order stiffer, couple of order of magnitude stiffer than the bending stiffness. Because here I need a stiff material to impose an equality in the other dots. So how do you choose that number? Well, in this case, I have something to the power of 10 for the Young modulus, but then I have something to the power of -4 for the bending stiffness, for the bending moment of inertia. So the bending stiffness will be something to the power of 6, okay? And then I add 3, 4 order of magnitudes. So I don't want to make this number much stiffer, because otherwise my model will be ill-posed. But it should be enough stiffer to impose a constraint. So let's say 2, 3, 4 order of magnitudes are fine. That's why I've chosen this one. Then we have the peak oriented that I've shown before. The parameters were chosen to match the one in ETABS. Then I have the zero length element property and the inch beam element property. Now, same thing here, I choose the elastic property, the zero length element property, and then I merge them together in the injet beam property, which is the one that I assigned to this beam here. Then everything is as before. So I have the two masses on top, I have the fixity at the bottom, the fixity at the top where only the x displacement is free. And then we have the recorder, conditions, we don't need the vertical load because we don't have any vertical load, and we don't need the wipe as before. Okay, so let's go to the time history analysis. Here I will give you the settings that are not working, okay? So when you do, if you have followed other of our webinars, we always were using displacement increment test with values that were to the power of -5, -6. And if you think about it, it may seem reasonable because you are modeling in meters. So you say for me, oh, just a small background for those of you who are not familiar with the convergence test. If you don't know, if you haven't done anything about nonlinear analysis, but basically, when you want to find the equilibrium, you want to find, for example, that the residual is zero or the increment in the solution vector is exactly zero. But as you know, from a computational point of view, it doesn't make sense to talk about exactly zero because there are round-off errors, so it's very difficult to find a real zero, almost impossible. So what you do, basically, you use a convergence test and a tolerance. When you choose a number here, basically you are saying that this number is so small that for you any quantity smaller than this number can be considered negligible or equal to zero, okay? So when I use this number for the displacement increment test, I'm saying that, for example, here I'm modeling in meters, 1 to the minus 6 meters, so it means 1 micrometer, for me is zero. And it makes sense because if you think 1 micrometer is the size of a cell, for example, so it's very small in terms of meters. But then there is a small problem here. When in OpenSees you talk about displacement increment, you're actually talking about the entire solution vector. So displacement is used in a general sense because it has both the displacement and the rotation in radians, okay? So sometimes this number is not sufficient because in this case you will see that will give me a non-equilibrated result, and I will show you why. And it was not easy to detect this error actually. So if I try to run the analysis, so it goes pretty fast, so you think it is converging. And if you look at this one, it is converging to values. Let me stop it to values, so to the minus 9, minus 10. So it seems pretty converging. So you may think, okay, everything was fine. I go here, I open the database for the plastic one, and I try to do some comparison with the elastic results, okay? So first of all, I want to export the results at the top node. Let me show the node. First of all, here, do not make the error of using the rubber band selection because here you have two overlapping nodes because here you have the plastic hinge, okay? So you can click on it, and since you have two overlapping nodes plus the zero length element, it will say what node do you want to select. Now in my case, I want to select node 2, the one with the smallest ID, because it's the one that you have in STKO, and it's the one where you apply the load, okay? So number 2, and here I want to extract displacement. Next, and I'm going to call this one UX plastic. I don't want to create another chart because I'm going to superimpose this one on the elastic response, okay? So I just want to generate it. So I go here and I click add, and I want to add the UX plastic. And as you can see, there is no difference from the elastic one. So you may say, okay, probably it happened because my model is still in the elastic regime. But then if you go back to the preprocessor and you go to the definition of the plastic hinge, here you see that the yield moment is about 110 units, okay? 110 Newton time meters, okay? If I plot it, okay? So this one should be my yield force. Now, if I go to the post-processor and I look at the elastic reaction force, you can see that at this point, it already reached the yield moment. So you expect that from this point on, so around time step 10, the plastic displacement will be much larger than the elastic ones. In this case, it is still elastic. So you may say, how can it happen? Because the reaction is so high, how it is possible that the displacement are still elastic? Okay, so you keep on investigating on what's going on. So you select the node at the bottom, node number 1, and say, okay, let's go and see the reaction forces. The reaction forces should be different also in this case, but then you can see that I choose reaction force along the x, and I call it fx plastic. I go to fx elastic and I superimpose the fx plastic. And also here you don't see any difference, okay? Okay, so you do the same with the bending moment, because now you may say, okay, for me this doesn't make sense, because if I have a bending moment which is higher, like the elastic one, because you say, okay, the displacement, the plastic displacement is equal to the elastic case, the reaction forces is equal. Since the bending moment are related to the shear forces by equilibrium, so I have to have the same values multiplied by 1.3. They are larger than the yield moment. So how can it happen? So you do the same. You go here and you try to export the reaction forces, the reaction moment, sorry. So reaction moment, this time about the y-axis, next. And I call this one my plastic. So I go here, I superimpose, I expect them to be elastic. But as you can see here, the reaction moment are very very low, and they are not even, they didn't even reach the yield stiffness. So you may think, okay, my model remained elastic, but it doesn't make sense, because as I told you, the bending moment, even if your model is elastic or plastic, the equilibrium is always the equilibrium. So the reaction moment should be, in this case, equal to the reaction forces times half of the height of this column. And in this case, it doesn't happen. So basically, what is happening? The problem is that then having a look at this, you already understand there is a problem of that your solution is not in equilibrium, okay? But your solution has been accepted by the convergence test. So you can soon arrive to the conclusion that your convergence test was not small enough. Okay, so it accepted a solution which is not actually in equilibrium. That's why you have this problem. So to solve this one, you have a couple of choices. You go back here and you can easily understand, because if you go to the spring and you look at stiffness and yield force, if you divide this one by the yield force, you have a yield rotation which is about 1 to the minus 7 or 1 to the minus 8. And it already can help you to understand what is the problem, because when you go to the convergence test, you have said that for me, anything smaller than 1 to the minus 6, in this case also rotation, are negligible. But actually this is not true, because 1 to the minus 7 was more than, was not negligible at all, because it is the yield rotation. So you have two options. One is to use the Norman balance test with values of 1 to the minus 3, which is fine in this case because it is 1 to the minus 3 newtons. The other choice is to keep the norm displacement, because, for example, you are using the penalty constraints and you cannot use the Norman balance. But in this case, you should use a value which is much smaller, like 1 to the minus 10 or 12, for example. Okay, now I try to run this analysis. Now it is going, but you can see that it has convergence problems, okay? So I can say, okay, let's try to stop it now. I don't want to waste time. You can try to use something different. You can try to use the Norman balance, or keep this one and use some other techniques. For example, in this case, with very stiff problems like this one, the Krylov Newton is much better than the Newton one. So I choose the Krylov. The Krylov Newton does not have a quadratic convergence, so you need to increase the number of iterations. For example, here I put 300, and let's see what happens. Okay, now as you can see, it is going. Let's see what happens when it reaches the plastic part. It is still going with some more iteration, and now it's stabilized. Okay, so now it seems it converged. So let's go back to the results, and we can just reload it. And now all the charts will be automatically updated, all the charts for the plastic part. Okay, so if we go back here, okay, here you can see that we have a much higher displacement. That probably is too high for what we expect, because we were using a check on the displacement. We need to make it smaller. So if we look at the displacement here, they're actually not matching the ones in ETABS. If we look at the force, we can see that here we had some convergence problem, and that the bending moments the same. Now, at least the force and the bending moments, they are related pretty well, okay? So we can see that up to here, we maintained a good equilibrium, but at a certain point, we accepted a wrong solution. And as you can see, I have a complete zero. So here I have two options. Once again, I can keep on decreasing the displacement because probably 1 to the minus 12 is still too high, or I can use the normal balance. Okay, now let's try to use the normal balance and let's see what happens. Basically, in this case, when you have stiff problems like this that are basically very stiff at the beginning and then very flat, probably using the normal balance is much better. Okay, so I just reload it. Okay, now it makes more sense. As I told you, after a displacement of 10, the elastic forces reached a value comparable to the plasticity at the hinge. And so it makes sense that you see this increased displacement due to the plastic rotation. Then the elastic force, they still make sense. They are much smaller than the other one. And the plastic moment as well. As you can see, they cannot reach, as you can see, when they reach their limit values, they are flat here. So they cannot go there. Okay, so this one makes sense. But I solved it using the normal balance. If you look at my presentation, I've shown you that if you use the penalty, and in very many cases, you are forced to use the penalty method, so you cannot use the normal balance. Well, in this case, you have to keep on decreasing the tolerance. So if I want to use the displacement increment test, probably 1 to the minus 12 is not enough, and I have to use 1 to the minus 14, for example. Let's see if it works. Now, as you can see, it is accepting a residual of 1 to the minus 17, sorry, residual of the displacement, 1 to the minus 17. So here probably should be the same result. Now it should not change. It should be equal to the results given by the normal balance. Okay, now this is fine. As you can see, there is not the error that we had before that the displacement was growing. The reaction forces are fine, and the bending moments are fine. Okay. So in this case, we managed to fix this problem. Now, with a last check, we want to check what's going on in the plastic hinge. Now, to see what's going on in the plastic hinge, you need another plot because you need a Gauss plot so that I can see the Gauss points of the plastic hinges. Now, for the plastic hinges, OpenSees call them stress. And since you have 6 components, STKO thinks that it is a stress tensor. That's why you see these numbers here. But actually, don't look at the numbers. You just consider that the 6 components are the first forces, X, Y, Z, and then 3 bending moments. So the value that I want to look at is the bending moment S23, which is the bending moment about the Y-axis. So I go in chart data. I want to extract a chart data from Gauss points. Next. Now I want to use a result versus another result. So in this case, I want to plot strain versus stress. And I choose the 5th component, which is the rotation about Y and the moment about Y. Next. And I have to choose the Gauss point. Well, I choose this one, but actually the result will be the same. So next, and this one is RY-MY plastic. And I want to create a chart for this. Okay, so this one is my hysteresis loop of my plastic hinge. Okay, so basically in this case I've shown you how to fix convergence problems, not when your model is not converging, which is what happens usually, but actually for a very different problem when your model converges to a wrong solution, which for me is much more dangerous than not converging, because when you converge to a wrong solution and you do not check that there is equilibrium, you don't do enough checks on the post-processor, you can think that your model is fine while it is actually completely wrong. Okay. So let's go back to the presentation. Now with this, we are done. So thank you everyone for following this webinar. And now we have some minutes for questions if you have any. Okay. So if you have any question, please go ahead with the questions. I stop my sharing so that I can see if you have any questions. How do we select parameters for norm unbalance test? Okay, so first question, how to select parameters for norm unbalance? Well, pretty much how you do it for the displacement. You have to think about a couple of things. So let me share my screen. When you choose the values for the norm unbalance, you have to take into account a couple of things. So as in this case, I was doing it for the norm displacement. Well, first of all, you have to keep in mind what are the units that you're using. So for example, in this case, I was using Newton and meters. So that's why I said for me, a check on the displacement equal to 1 to the minus 6 is fine because it's 1 to the minus 6 meters. But then I made a mistake because in this model, I'm also using rotations. And for me, a rotation of 1 to the minus 6 was not small enough. Okay, it was very large. That's why I have to change it. When you go to the norm unbalance, it's the same thing. So here you have to think about that this vector has forces and moments. Now the forces have the order of magnitudes are made in newtons, and the moments are Newton meters. Okay, so you have to think about what is for me a small enough force. 1 to the minus 3 meters is small enough for me. Yes, 1 to the minus 3 newtons times meter is small enough. And you may say, okay, yes. But basically depends on what you're modeling, because if you're modeling a very small part where a moment of 0.01 is enough, is very large, then this one is not good for you, okay? So it's always based on the model that you're doing with the units that you're doing, okay? So keep in mind that this one is a number that for you is negligible in the vector that you're looking at. So for me, 0.01, any quantity in the unbalanced vector is small. But it depends on the problem, so there is not a unique number, okay? So first of all, keep in mind what are the units. Keep in mind if you're using only displacement and forces or also rotation and moments, because they have different units. That's the main problem, because when you check the unbalance or the displacement vector, one thing is that you have only displacement and forces. So they have meters and force, length and forces as units. When you have also rotation and moments, in the same vectors, you have different quantities. So you have to think about that this one should be small for both, in this case, forces and moments, not only for one of them, which is the error that I made before. When I've said, okay, for me, 1 to the minus 6 meters is fine, I forgot that in the same vector, I also had rotations, okay? So this is the main way to understand how to choose those values. Is there any other question? Okay, I have okay. By Dennis, what about relative types testing? Which case they are more relevant? Okay, so there is this other question about the relative tests. The explanation that I've given now, let me share my screen once again. Okay, so this second question, what about relative tests? What I've said now is that the norm unbalance, the norm displacement, and the energy increment test, both of the three of them are based on absolute values, okay? So that's why I said you have to take care about the units that you're using. If you don't want to take care about the units, there is another choice. You can choose what are called the relative tests. That can be, for example, relative norm unbalance, relative norm displacement, or relative energy increment. What does it mean, relative? For example, when I use norm unbalance, it says that for me the convergence is reached when the norm of my residual vector is less than this value. But if I choose the relative norm unbalance, where is it? I'm saying, and I choose 1 to the minus 3, for example, so here. In the relative case, I'm saying that my convergence has been reached when the error at the current step is 0.001, the error at the beginning of the step. So it is relative. In this case, you are removing the problems of the unit system, okay? So the relative tests are very fine because you don't have to care about the size of your model. because for me, reducing the error from the start of the step to the end of the step of 1000 time is always a good choice, okay? Because the error is very small at that point. There is only one problem. When you're using very tiny time steps, for example, because you're doing very nonlinear dynamic analysis, if you're doing very tiny time steps and the first error at the beginning of the step is very small, it will be very difficult for OpenSees to lower that value of 1000 times. So you have an advantage sometimes, but with very small time steps, the relative norm is not advantageous. In fact, actually, in the next days, we will code something for OpenSees, which is a mix of relative and absolute test. That would be the best choice. So you use the relative test, and if the relative does not converge, which means for very small values, you use the absolute test. So for the moment, the only thing that you have to take care about is that the relative is fine because you don't care about the units. But if you're doing very nonlinear analysis with very small time step, they will almost not work. So that's why I prefer to use the absolute checks and take care about what is the unit system that I'm using. Okay. So we have another question. Can you explain how to choose the penalty parameters again? Okay, so the penalty parameters, there is one formula. Let me use the, oops, I want to share the screen again. I just want to use an annotation, okay. Now, let's say you have your stiffness method. The idea is this, okay, let's say that K E E is the largest value on my system matrix. So I have my system matrix, which is very large. I have a lot of values here and there. The largest value on the diagonal is this value here, okay? Then I will explain you how to identify it, because when you have a very complex matrix, you may say, how do I identify the largest value of my stiffness matrix? Well, it is not necessary that this one should be the largest exact value. You just need the order of magnitude. So later on, I will explain you how to identify this one. But let's say you have the largest value on the diagonal of my complete system matrix. Then you have to choose the order of magnitude of this one. Let's call it O. And O can be a function like, this one should be the round, or you can use ceiling. So if you're in MATLAB, you can write sail of log 10 of KEE. Okay, so this function here will give you the order of magnitude. Basically, if this one is 2 to the power of 6, the order of magnitude here will be 6, okay? So it's very easy to identify. If you want a function that does it automatically, you can do this one. But actually, it's very easy to do it by hand, just by looking at the values, okay? So when you have the order of magnitude, you should say the penalty parameters should be equal to 10 to the power of this order of magnitude plus 8. Why 8? It's not just a magic number. In computers, a floating point, which is a real number, is represented with 16 significant digits. So it cannot be exact, arithmetically precise. There is a finite precision for floating point numbers, and 16 is the number of significant digits. Why you choose the 8? Well, because the penalty parameter, in theory, it should be large enough to impose the displacement, but not so large to make the system singular. So basically, in theory, I should use a value which approaches infinite to apply the constraint. But if I use an infinite value in real-life applications, my matrix will be singular. So someone said, okay, let's do something in between. So let's take half from the precision of the constraint and half from the precision of the computer. So that's why you choose 8, because it is half the number of significant digits of a double, okay? So basically, if you have a problem like this one, for example, let me stop the annotation. If you are here, now the problem is that how do you identify this one? Well, I cannot identify it exactly, but as you can see, I just need the order of magnitude. So, for example, in this case, I know that my problem is bending dominated because I'm looking at the bending stress here. So I go to the section and I say, okay, I have a Young modulus, which is the power of 10. Then I have a rectangular section whose bending inertia is to the power of -4. So in this case, it's 10 minus 4. The entire stiffness EJ will be to the power of 6. Then I take 6 plus 8, and I use 1 to the power of 1 E14, for example. Then it should not be exactly that value. It can be 1 order of magnitude more, 1 order of magnitude less, but not much different than that one, okay? When you have, since you do geotechnical analysis, so you use mesh models, don't take exactly the Young modulus. For example, if you are modeling a soil, you take the Young modulus and you multiply it by the volume of the element, for example. That one can be a sufficient realistic number for this value here, okay? So let me just clean the annotation. Okay. Is there any other questions? Okay, I think we are done. There are no other questions. Let me stop sharing my screen. Yeah, I need to upgrade my Dropbox. Okay, so if there is no other question, I would like to thank you for taking part to this webinar, and see you in the next webinars. Okay, so always have a look at our webpage. We're going to give free webinars every month, and by tomorrow you will have the recording of this webinar and all the input file. Okay, so thank you everyone.